Hello everyone. Today I am going to discussing about stereochemistry and structural elucidation of cholesterol. Cholesterol is the most important animal steroid from which other steroid compounds are formed. Cholesterol is widely distributed in animal tissues. Cholesterol is a clinically significant steroid. Level of cholesterol in blood is related to the development of atherosclerosis and myocardial infarction. Abnormality in cholesterol metabolism may lead to cardiovascular accidents and heart attacks. Cholesterol is incorporated in nerve conduction and glucocorticoid androgens, estrogens are formed from cholesterol. Vitamin D3 is formed from 7-dehydrocholesterol. Bile acids and bile salts are derived from cholesterol. Structure of cholesterol is given here. Molecular formula of cholesterol is C27H46O and its molecular weight is 386.7. IUPAC name is cholest 5 in 3 beta ol. Cholesterol is composed of 4 rings. These rings are designated as A, B, C, D or 1, 2, 3, 4 beginning from the 6-membered ring on the left. It should be noted that the nucleus contains 2 angular methyl group, one at 10th carbon and the other at 13th carbon. Now let's move into the structure of nucleus. First, structure of the ring system. Under this heading, we shall deal with the nature of ring system present in cholesterol. The usual test for functional groups showed that cholesterol contained 1 double bond and 1 hydroxyl group. The reaction is given here. Cholesterol is converted to cholestanol on treating with H2PT and this cholestanol is converted to cholestanone on treating with chromium trioxide. This cholestanone is converted to cholestane. It's a saturated hydrocarbon on treating with a zinc amalgam in presence of HCl. Conversion of cholesterol into cholestanol shows the presence of 1 double bond and oxidation of cholestanol to cholestanone shows that cholesterol is a secondary alcohol. Cholestane is a saturated hydrocarbon and corresponds to the general formula CnH2n-6 and consequently it's a tetracyclic. Thus, we can conclude that cholesterol is tetracyclic compound. Now, let's check the position of hydroxyl group and double bond in cholesterol. Consider the following reaction. Here, the cholestanone is converted to dicarboxylic acid on treating with the nitric acid. And this dicarboxylic acid is converted to ketone on heating at 300 degrees Celsius. Since the dicarboxylic acid contains the same number of carbon atoms as the ketone from which it is derived, the keto group in cholestanone must be therefore be in a ring. Also, the pyrolysis of dicarboxylic acid produces ketone with the loss of one carbon atom. It therefore follows from Planck's rule that ketone is either 1:6 or 1:7 dicarboxylic acid. Now, we have seen that nucleus contains 3 6-membered ring and 1 5-membered ring. Thus, the dicarboxylic acid must be obtained by opening of ring A, B or C and consequently it follows that the hydroxyl group in cholesterol is in the ring A, B or C. Actually, 2 isomeric dicarboxylic acids are obtained when cholesterol is oxidized. The formation of these 2 acids indicates that the keto group in cholesterol is flanked on either side by a methyl group. Simply, the group CH2COCH2 is present in cholesterol. Examination of the reference structure of cholesterol shows that such an arrangement is possible only if the hydroxyl group is in the ring A. The reaction is given here. Cholesterol is converted to cholesterol triol on treating with the hydrogen peroxide and acetic acid, which is converted to hydroxycholesterol on treating with the chromium dioxide. This cholesterol is converted to tetracarboxylic acid on treating with the chromium trioxide. In the conversion of cholesterol into cholesterol triol, the double bond in cholesterol is hydroxylated. Since only 2 of the 3 hydroxyl groups in cholesterol triol are oxidized to produce hydroxycholesterol. These 2 groups are secondary alcoholic group, and the third being resistant to oxidation is probably a tertiary alcoholic group. Dehydration of hydroxycholesterol and the subsequent reduction of the double bond forms cholesterol, and this on oxidation gives tetracarboxylic acid without the loss of carbon atoms. Thus, the 2 keto groups in cholesterol must be in different rings. The hydroxyl group and double bond in cholesterol must be in different rings. The position of hydroxyl group at position 3 is proved by reducing cholesterol to cholestanol, oxidized to cholestanol, then it treated with the selenium. Reaction may be formulated as follows. Reaction is given here. Now let's move into the nature and position of the side chain in cholesterol structure. Acetylation of cholesterol produces cholesterol acetate, and this on oxidation with the chromium trioxide forms a steam volatile ketone and the acetate of the hydroxy ketone. The ketone was shown to be isohexyl methyl ketone. Thus, this ketone is the side chain of cholesterol, the point of attachment of the side chain being at the carbon of the keto group. These results do not show where the side chain is attached to the nucleus of cholesterol, but if we accept that the position at 7, then we can formulate the reaction as follows. The reaction is given. Now let's move into the position of the 2 angular methyl groups in the structure of cholesterol. The cyclopentanophenolamine nucleus of cholesterol accounts for 17 carbon atoms and the side chain for 8. Thus, 25 carbon atoms in all have been accounted for. But since the molecular formula is C27H46O, 2 more carbon atoms must be fitted into the structure. These 2 carbon atoms have been shown to the angular methyl group. In elucidating the position of the hydroxyl group and double bond, one of the compound obtained was a keto acid. This compound, when subjected to Clemmenson reduction and followed by 2 Barbier-Weinland degradation, gives an acid which is very difficult to esterify and evolves carbon monoxide when warmed with concentrated sulfuric acid. Since these reactions are the characteristic of an acid containing carboxyl attached to a tertiary carbon atom. Now let's move into the stereochemistry of cholesterol. First, configuration of cholesterol. The structure, numbering and IUPAC name of cholesterol is given here. There are 8 asymmetric carbon atoms are present in the nucleus at the position 3, 5, 8, 9, 10, 13, 14 and 17. Thus, 256 optical isomers are possible if we include the asymmetric carbon in the side chain at the position 20. Then there are 512 optical isomers are possible. Stereoisomerism of the steroids is conveniently classified into 2 types. One dealing with the way in which the rings are fused together, and the other with the configuration of subsequent groups, particularly those at the 3rd carbon and the 17th carbon. Now let's check the configuration of nucleus. There are 6 asymmetric carbon atoms in the nucleus at the position 5, 8, 9, 10, 13 and 14. And therefore 64 optically active forms possible. X-ray analysis shown that the steroid molecules is long and thin. The molecule is so essentially flat. This is only possible if the rings B and C are fused together in a trans manner. Rings A or B and C or D could be cis or trans. It has been found that all naturally occurring saturated steroids except those of the heart poisons belong either to the cholesterol series or to the coprostein series. In the former, the rings A or B are trans and in the later cis. The rings B or C and C or D being trans in both series. By convention, the methyl group at 10th position, methyl group at the 10th carbon in the cholesterol has been placed above the plane of the molecule, and therefore this leads to 4 possible stereoisomers of cholesterol. Those 4 possible isomers of cholesterol are given here. Cholesterol and a coprostein structure are given here. Now let's check the configuration of substituent group in the structure of cholesterol. By convention, the hydroxy group at the 3rd carbon in cholesterol is taken as being above the plane. The hydroxyl group is taken as being in the cis position with respect to the methyl group at the 10th carbon. This configuration occurs in all natural steroids and give rise to the beta series. The prefix beta indicating that substituent group lies above the plane of molecule. When the hydroxyl group lies below the plane, the compounds are said to belong to the alpha or epi series. The prefix epi indicates the epimer due to the inversion of configuration at the 3rd carbon. Stereochemical relationship of steroids to D plus glyceraldehyde proved by degradation of cholesterol to derivatives of citronellal. Correlation of configuration in steroid has been carried out by the method of rotatory dispersion. Saturated steroids have been examined and the results shows that as the position of the carbonyl group changes in A or B trans steroids, the curve changes in sign, shape or amplitude. Therefore, this method may be used to locate the unknown position of carbonyl group in steroid, and shape of the curve depends on the conformation of molecule. Therefore, by comparing the curve of compound with that of a compound of non-absolute configuration and containing carbonyl group in the same position, it is possible to deduce the absolute configuration of a group in the unknown compound. Reference is given here, and thanks for watching.